Welcome to Python Algorithms. This video is the complete guide to searching every major algorithm from linear search all the way up to binary search on the answer space, 2D matrix search, hash-based lookup, and the built-in Python tools that do the heavy lifting for you. By the end, you'll know not just how each algorithm works, but exactly when to reach for each one. Next, searching is the process of locating a target value, the key, within a collection of data. It sounds simple, but searching is one of the most executed operations in computing. Databases run billions of queries per second. File systems look up paths millions of times a minute. Every Python dictionary lookup is a search. Getting this right matters. Click. The landscape splits into four broad regimes. Unordered data with no pre-processing. Linear search, ON. Sorted arrays. Binary search, O, log n. Hash tables, O1, average. Tree structures like BSTs and heaps, O log n. The regime you're in determines which algorithm is even applicable. Click before choosing an algorithm, 4 questions. Is the data sorted? Sorting unlocks O, log n. Is data in memory or on disk? Disk I/O changes the cost model. Block reads make B trees the standard. How often is data modified versus searched? High modification frequency means maintaining a sort or hash is expensive. Do you need the index or just a boolean? Some APIs return one, some the other. Click the decision tree on the right, maps these questions to algorithms. Unsorted right pointing arrow linear search. Sorted plus uniform distribution, right pointing arrow interpolation search. Sorted plus unknown size right pointing arrow exponential search. Sorted otherwise right pointing arrow binary search. We'll walk every one of these branches in this video. Linear search is the simplest possible algorithm. Scan every element from left to right until you find the key or exhaust the array. No preconditions. Works on sorted, unsorted, or any collection at all. Click. The basic implementation is 2 lines of logic. Iterate with enumerate, compare, return the index on a hit, return -1 at the end. Clean and universal. Linear underscore search, underscore, all returns every index where the key appears, useful when duplicates exist. A list comprehension does it in 1 line. Sentinel search is a micro-optimization. Normally the inner loop checks 2 conditions. Has I reached the end, and does the current element match? By appending the key itself to the end of the array before scanning, we guarantee the key is always found eventually, eliminating the bounds check. That's 1 fewer comparison per iteration. On modern CPUs, the difference is marginal, but the technique shows up in textbooks and is worth knowing. Click the trace diagram shows key equals 22 in 64, 25, 12, 22, 11. 4 comparisons before finding it at index 3. If the key were 11, that's 5 comparisons. If the key isn't present, you scan the whole array ON. Click best case O1, first element. Average ON/2, which is still ON. Worst ON, space O1. Click the callout worth internalizing. Python's in operator on a list and list.index are linear searches underneath. ON, every time. If you're doing repeated membership tests on a large list, convert it to a set first and get O1. Next. Binary search is the workhorse algorithm for sorted data. Every step halves the search space, giving O log n regardless of data size. Click the recurrence confirms it. T of n equals T of n/2 plus O1 resolves to O log n. That log base 2 growth is extremely slow. 1 billion elements requires at most 30 steps. Click the iterative implementation maintains 2 pointers, low and high, defining the active search window. At each step, we compute mid equals low plus high low /2. The parenthetical form matters. In Python, overflow isn't an issue, but in C, Java, or C++, the naive low plus high /2 can overflow when both values are large. The safe form is a habit worth building. 3 cases. Midpoint equals key, return it. Midpoint less than key, key must be in the right half. Advance low to mid +1. Midpoint greater than key, key must be in the left half. Retreat high to mid, 1. If the loop exits without a match, return -1. Click the search trace shows key equals 23 in a 10-element array. Step 1. Mid is index 4, value 16. 16 is less than 23, so low moves to 5. Step 2. Mid is index 7, value 56. 56 is greater, so high moves to 6. Step 3. Mid is index 5, value 23. Found it in 3 steps instead of the worst case 10. Click the bisect module is Python's standard library binary search. Bisect underscore left returns the leftmost insertion point for a key. Bisect underscore right returns the rightmost. To check presence, use bisect underscore left, and then verify the value at that position. Bisect.insort inserts a value, while keeping the list sorted. These are implemented in C, and are the recommended approach for binary search on sorted Python lists. Click the off by 1 callout, Always use low less than equals high, with a strict less than or equal. If you use low less than high, you miss the case where exactly one element remains. And always use mid plus 1/mid 1 when updating the bounds, not just mid, or you'll loop forever. Next. The recursive formulation of binary search maps more directly to its mathematical definition. Same logic, different style. Click binary underscore search underscore rec takes low and high as default arguments, defaulting to the full array on the first call. Base case, low greater than high. The window is empty, return -1. If high is not provided, initialize it to the last index. Then the same three-way comparison as the iterative version, but each branch returns a recursive call instead of updating a pointer. The recursive version uses O log n call stack space. Each recursive call adds a frame. The iterative version uses O1 space, no stack frames. For production code, prefer iterative. For learning and for interview whiteboards where clarity matters, recursive is fine. Click the call stack diagram, shows key equals 38. 4 recursive frames, starting at full array, narrowing right, narrowing left, finding it. Each frame represents one halving of the search space. Click the generic binary search on conditions template at the bottom, is the most powerful pattern in this whole video. Sometimes you don't want to find a value in an array. You want to find the leftmost index where some Boolean condition becomes true, given that the condition is monotone, false, 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 true, true, true. The template binary searches for that transition point. This template is the foundation for binary search on the answer space, which we'll see shortly. Next. Standard binary search finds a matching index. These variants find the first, the last, and the count, and handle arrays that have been rotated. Click first occurrence with duplicates. The modification: when we find a match, don't immediately return. Record the index as a candidate, but then continue searching left. High equals mid 1. Keep narrowing until the window collapses. The last recorded candidate is the leftmost match. Last occurrence is symmetric. When we find a match, record it, and continue searching right. Low equals mid plus 1. The last candidate is the rightmost match. Count occurrences is then trivial. Last, first, plus 1. 2 binary searches instead of 1 linear scan. O log n total. On 1, 2, 2, 2, 3, 4, 5. First occurrence of 2 is index 1. Last is index 3. Count is 3. Click search in a rotated sorted array. Take a sorted array and rotate it at some pivot. 0, 1, 2, 4, 5, 6, 7. Becomes 4, 5, 6, 7. 0, 1, 2. Standard binary search breaks because it assumes the whole array is sorted. The fix exploits this key insight. Even in a rotated array, exactly one of the two halves is always properly sorted. Check which half is sorted by comparing arranged by to arranged by mid. Then check if the key falls within that sorted half. If yes, recurse into it. If no, recurse into the other half. O log n preserved. Click. The callout restates the insight. At every step, one half is guaranteed to be sorted. Identifying which half, and using the sorted half's bounds to decide where the key falls, is the entire algorithm. This is the conceptual breakthrough that turns binary search from an array lookup algorithm into a general optimization tool. The idea: instead of searching for a value in an array, we're searching for the minimum feasible answer in a range of possible answer values. We binary search on that range, and at each midpoint we ask, is this answer feasible? If yes, try smaller. If no, try larger. As long as the feasibility function is monotone, feasible for all values above some threshold, infeasible below it, binary search finds that threshold in O-log range, feasibility checks. Click. Coco eating bananas is the classic example. Coco must eat all piles within h hours. We want the minimum speed k, in bananas per hour. The answer lies somewhere between 1 and the size of the largest pile. For any candidate speed k, can underscore finish k checks whether k is sufficient in ON. Binary search on k gives ON log max pile, overall, far better than checking every possible speed linearly. Notice the loop condition is low less than high rather than low less than equals high, and when feasible we set high equals mid, rather than mid, 1. This is the leftmost feasibility template. It converges to the smallest value where the condition holds. Click minimum days to make bouquets, follows the identical template. We binary search on the number of days. The feasibility check scans the bloom array counting consecutive runs of flowers that have bloomed by that day. Different problem. Identical template structure. Click the flow diagram. Encodes the template visually. Define range. Compute mid. Check feasibility. Shrink accordingly. Converge to low. Click the problem table gives 4 canonical examples. Cocoa bananas, split array largest sum, ship packages within D days, and integer square root, all reducible to the same template. When you see minimum maximum or maximize minimum in a problem statement, think binary search on the answer space. Next. Jump search occupies the middle ground between linear and binary on sorted arrays, but its real strength is on systems where backward movement in memory is expensive. Click. The algorithm moves forward in fixed-size blocks of square root n elements at a time. It jumps until it finds a block where the last element is greater than or equal to the key. Then it does a linear scan backward within that block. Because we only ever step backward within one block, square root n steps, and we made it most square root n jumps to get there, the worst case is O square root n plus square root n equals O square root n. The optimal block size is mathematically derived. Total cost is n/step jumps plus step linear steps. Minimize by taking the derivative with respect to step, equate to 0, and you get step equals square root n. For n equals 1 million, that's a block size of exactly 1000. Click. The search trace shows key equals 55 in a 15-element Fibonacci array with block size 4. Jump to index 3, value 2, too small. Jump to index 7, value 13, too small. Jump to index 11, value 89, too large. Stop. Linear scan from index 8 backward. 21, 34, 55 found. Click the comparison chart, makes the gap concrete. For n equals 10,000, linear search, worst case 10,000 steps. Jump search 100 steps. Binary search 14 steps. Jump is much better than linear, but doesn't approach binary. Use jump search when the collection is stored on a sorted medium, where forward seeks are cheap, but backward seeks are expensive. Tape storage being the canonical historical example. Next. Binary search always probes the middle. Interpolation search is smarter. It estimates where the key is based on its value relative to the endpoints, the way you'd flip open a phone book at roughly the right spot for a name starting with W rather than opening it in the middle. Click the probe formula. Pus equals low plus floor. Key, arranged by, times, high-low, arranged by. This linearly interpolates the expected position, based on where the key's value falls proportionally within the current range. On a uniformly distributed array, this estimate is extremely accurate, giving O log n, average case, successive squarings rather than halvings. Click the code. The while condition includes arranged by, less than equals key, less than equals arranged by. If the key is outside the current range, it's not present. On each iteration, compute pos with the interpolation formula, then the same three-way comparison as binary search. The key difference, POS is not fixed at the midpoint. It jumps to the estimated location. Click the comparison diagram shows key equals 70 in a uniform array from 10 to 100. Binary search always probes index 4 first, value 50. Interpolation probes index 6 directly, value 70. Found in one step. Click the warning is important. Interpolation search degrades to ON worst case on non-uniform data. A skewed distribution, exponential spacing, lots of duplicates or adversarial inputs, gives terrible probe estimates, and you end up scanning the whole array. Unless you know your data is uniformly distributed, binary search is guaranteed O log n is safer. Exponential search solves a specific problem. Binary search can't. What do you do when you don't know the array's size, or when the key is likely near the beginning? Click. The algorithm has two phases. Doubling phase. Start at index 1, double the index repeatedly. 1, 2, 4, 8, 16. Until you either reach the end of the array, or find a value greater than or equal to the key. Binary search phase. Apply standard binary search in the range I/2, min, I and 1. The doubling phase costs O log p, where p is the key's actual position. The binary search within that range also costs O log p. Total, O log p. If the key is at position 5, exponential search costs log 5, about 2 to 3 steps to find the range, then a few more for binary search. Standard binary search on a million-element array would always take 20 steps regardless of where the key is. Click the trace diagram shows key equals 10 in an array, doubling through indices 1, 2, 4, 8. Value at index 8 is 160, which exceeds 10. Binary search in the range from 4 to 8. Found value 10 at index 5. Click the comparison table makes the use case clear. When the key is near the beginning of a large array, exponential search dominates. When the array is unbounded or streamed, you don't know n, exponential search is the only correct approach. The unbounded underscore search function in the code handles index error from the stream, adjusting bounds accordingly. Next. Ternary search divides the search space into 3 parts. On sorted arrays, this is actually worse than binary search despite the smaller number of iterations, and it's worth understanding why. But on unimodal functions, ternary search is the correct tool. Click Apply to a sorted array. Divide with 2 probe points, T1 and T2, each 1/3 of the way from the ends. Eliminate the outer third that doesn't contain the key. This gives O log 3n iterations. but each iteration requires 2 comparisons, not 1. Log base 3 of n is about 0.63 times log base 2 of n, fewer iterations. But 2 times 0.63 is 1.26, more total comparisons than binary search's 1 comparison per iteration. Binary search wins on arrays. Click the real use case is finding the maximum or minimum of a unimodal function. Any function that increases monotonically, reaches a single peak, then decreases monotonically. At each step, compute fm1 and fm2 where m1 and m2 divide the interval into thirds. If fm1 less than fm2, the maximum is in the right 2/3, set low equals m1. Otherwise it's in the left 2/3, set high equals m2. Repeat until the interval is smaller than epsilon. The example function made if x3 squared plus 9 has its maximum at x equals 3. Ternary search converges to exactly that. Click. The math on the right explains the binary vs ternary comparison concisely. Remember, for arrays, use binary. For unimodal optimization, ternary search is the standard. Fibonacci search is a curiosity with a practical niche. It performs binary search-style narrowing using only addition and subtraction, no division. That makes it valuable on embedded systems, or historical hardware, where division was expensive. Click the setup. Find the smallest Fibonacci number that is greater than or equal to n, the array size. Use the 2 smaller Fibonacci numbers as the split denominators. The offset variable tracks how much of the array we've already eliminated. Each iteration probes at min, offset plus fib2, n1. If the element there is less than the key, advance the offset and drop to the next smaller Fibonacci triplet. If greater, drop down without moving the offset. If equal, return the position. Click the trace shows key equals 85 in an 11-element array. Start with Fibonacci triplet, 5, 8, 13. Probe at index 7, value 82, too small. Advance offset to 7. Probe at index 9, value 90, too large. Probe at index 8, value 85. Found. Click the comparison table. Binary search uses division by 2. Fibonacci uses only addition and subtraction. The base of the logarithm is phi. The golden ratio approximately equals 1.618, rather than 2, since Fibonacci numbers grow as phi to the power of n. Log base phi of n is about 1.44 times log base 2 of n. Fibonacci does slightly more iterations than binary, but avoids division entirely. In practice on modern hardware, binary search is faster. On certain embedded targets, Fibonacci search is the standard choice. Next. Searching extends naturally to 2 dimensions, and the approach differs based on the matrix's sorting structure. Click staircase search for a matrix where every row is sorted ascending, and every column is sorted ascending. Start at the top right corner, index, row 0, last column. From there, the element to the left is smaller, the element below is larger. This makes every comparison decisive. If the current element is greater than the key, move left, eliminating the current column. If it's less than the key, move down, eliminating the current row. If equal, found it. Each step eliminates either a full row or a full column. Maximum steps. M rows plus n columns equals O m plus n. Click Y top right specifically. It's the only corner with a guaranteed smaller neighbor in one direction and a guaranteed larger neighbor in the other. Top left, both left, out of bounds, and up, out of bounds. No valid moves. Bottom right, both larger neighbors already eliminated. Top right gives you exactly the monotone decision structure you need. Click the trace shows key equals 5 in the 5 times 5 matrix. Start at 0, 4, equals 15, too big, move left. 0, 3, equals 11, too big, move left. 0, 2, equals 7, too big, move left. 0, 1, equals 4, too small, move down. 1, 1, equals 5, found. 5 steps. Click flat binary search for a fully sorted matrix, where each row's last element is less than the next row's first element. Treat the entire matrix as a single sorted array. A flat index, mid maps to row and column, via divmod, mid, cols. Standard binary search on the flat index. O, log, m times n. Next. Hash-based search with Python's dict and set is the fastest possible lookup O1 average, and it's what you should reach for when doing repeated membership tests on large collections. Click the diagram explains how. A key is passed through a hash function that computes an integer. That integer is reduced to a valid array index with modulo. The value is stored at that bucket. Lookup follows the same path. Hash the key, modulo to get an index, check the bucket. No iteration needed. Click dict membership within is O1. Dict.get, with a default, avoids key error. Set membership is O1. These are the data structures to use for any does this exist problem with repeated queries. Click toSum is the canonical hash search pattern. For each number, compute the complement, the value that would pair with it to reach the target. Check if the complement has been seen before. If yes, return those two indices. ON total, with ON space for the seen dictionary. Without hashing, the naive two-loop approach is ON squared. Click subarray sum equals k, uses the prefix sum plus hash map pattern. Store how many times each prefix sum has been seen. For each new prefix sum p, check if pk exists in the map. If so, there are that many subarrays ending here with sum exactly kon time and space. Longest consecutive sequence converts the array to a set, then for each number that is the start of a sequence, no n1 in the set, walks forward counting the consecutive run. On overall, despite the nested while loop, because each element is visited at most twice. Click the comparison table. Hash is O1 for exact lookup but can't do range queries or ordered iteration. Binary search maintains order and supports range queries, but is O log n. Choose based on what your problem needs beyond membership. When data lives in a sorted structure, BST, sorted list, or heap, search exploits the structure's ordering property. Click BST search is OH, where H is the height. Iterative version. At each node, compare the key. Less than current value, go left. Greater, go right. Found or null, stop. On a balanced BST, H is O log n, giving O log n search. On a degenerate BST, sorted insertions, H is ON. Click sorted containers.sorted list. Is the Python standard for a balanced sorted collection. Index 7 returns the position in O log n. Bisect underscore left gives the insertion point. IRange 3, 7 returns all elements in a range, something a hash table cannot do. Use sorted list when you need sorted order with O log n, inserts and deletes. Click heap q gives O1 minimum access. Heap 0 is always the minimum. N smallest k and n largest k are ON log k. The heap doesn't support arbitrary search. You can only efficiently retrieve the minimum or maximum with negation. BST floor and ceiling, BST underscore floor, finds the largest value less than or equal to the key. Walk right when the current value is smaller than the key, tracking it as the best floor candidate so far. Walk left when larger. Returns the last tracked candidate. Click. The BST search path diagram traces key equals 6, start at root 8, 6 is less, go left to 3, 6 is greater, go right, found 6 in 3 comparisons. The comparison table summarizes all sorted structures. A sorted list has O log n search, but ON insert / delete. Dict / set are O1, but unordered. Balanced BST and sorted list give O log n for all 3 operations. Heap gives O1 minimum, but O log n, everything else. Next, Python ships with a complete toolkit for searching. Let's inventory it. Click List Methods. lst.indexx returns the first index of x, raises value error if not present, so guard it. X in LST is ON, linear scan. LST count x counts occurrences, also ON. Min and max, with a key function, find the element with the minimum or maximum of that attribute ON scan, with a configurable comparator. Click Next, with a generator expression, is the idiomatic Python short-circuit search. Next of x for x in nums, if x%2 equals 0, none. Finds the first even number and stops immediately. It doesn't build the full list. The second argument to next is the default if the generator is exhausted. This pattern is cleaner and more Pythonic than an explicit for loop with a break. Click Bisect module. Always use this for binary search on sorted lists rather than implementing it yourself. Bisect underscore left and bisect underscore right return insertion points in O log n. To check presence, get the insertion point, then verify the value at that position. Bisect.insort inserts while maintaining sorted order in ON time. The search is O log n, but the insertion shifts elements. Click Filter, Any. All are functional search tools. Filter, pred iterable, lazily produces matching elements. Any short circuits on the first true O1, in the best case. All short circuits on the first false. Both are ON worst case. re.search and re.findAll search within strings, using regular expression patterns. re.search finds the first match anywhere in the string. re.findAll returns all non-overlapping matches as a list. pathlib.path.glob, n.arglob do. Pattern-based file system search. Glob for one directory, arglob for recursive. Next. 3 advanced problems that showcase binary search in less obvious applications. Click Find Peak Element. A peak is any element greater than both its neighbors. The array may have multiple peaks. Find any one. The binary search works because, at any midpoint, if nums greater than nums mid plus 1, the left half contains at least one peak, either mid itself or something to its left. If nums less than equals nums mid plus 1, the right half contains at least one peak. This monotone property lets us binary search for a peak in O log n, without the array being sorted at all. Click Find Range, First and Last Occurrence. Rather than two separate first underscore occurrence and last underscore occurrence functions, this version unifies them with a go underscore left parameter. Finding the first occurrence, match, then keep searching left. Finding the last, match, then keep searching right. Returns, first underscore index, last underscore index, in O log n. Total with 2 passes. Click Median of two sorted arrays is the hardest problem on this slide. O log min, mn. The key insight. Finding the median is equivalent to finding a partition of the combined array, such that everything on the left is smaller than everything on the right, and both sides have equal, or off by 1 size. Binary search on the partition point, in the smaller array. For each candidate partition in A, compute the corresponding partition in B. Check if the partition is valid. The left side of A doesn't exceed the right side of B, and vice versa. Adjust accordingly. When the partition is valid, compute the median from the 4 boundary values. Click integer square root via binary search on the answer. Binary search in 1, x/2, for the largest midpoint whose square doesn't exceed x. When the loop exits, high is the floor of the square root. O log x. A clean demonstration that any monotone condition over a range can be binary searched. Next. Full reference table. All algorithms compared. Click starting from the top. Linear and Sentinel. ON worst case, O1 space. No sorting required, your baseline. Binary iterative. O log n. Worst case, O1 space, requires sorted. This is your default choice for sorted data. Binary recursive. Same time. O log n. Space for the call stack. Jump. O. Square root n. Interpolation. O. Log n. On uniform data, but ON worst case. Powerful but fragile. Exponential. O log p. Where p is the key's position. Excellent. When key is near the start, or array is unbounded. Fibonacci. O log n, but base phi rather than base 2. About 1.44 times more iterations than binary, but division free. Ternary. O log n. On arrays, use binary instead. Use ternary for unimodal function optimization. Hash. O1. Average ON. Worst case from collision. ON space overhead. BST balanced. O log n. For all operations. Click the bar chart. Makes the practical difference visceral. For 1 million elements. Linear needs up to 1 million comparisons. Jump needs 1000. Binary needs 20. Interpolation on uniform data needs about 5. Hash needs 1. The algorithmic choice matters enormously at scale. Click 2D matrix search summary. Row and column sorted matrix uses staircase search at OM plus n. Fully sorted matrix, row concatenation, uses flat binary search at O log mn. Unsorted matrix requires linear OMN. Python built-in operations. X in list is ON. X in set and X in dict are O1. List.index is OMN. Bisect.bisect is O log n. The decision tree on this slide is your reference for choosing the right search algorithm in any situation. Click Start at the top. How often are you searching? Once or rarely. Is the data sorted? No. Linear search. Yes. Binary search. Many times. Worth investing in pre-processing? Sort once, then use binary for O log n per query. Build a hash table for O1 per query. No pre-processing. Linear at ON. Still fine for small n below about 20 elements. From binary search, the branching special cases. Need first or last occurrence among duplicates. Modified binary search. Rotated array. Rotated binary search. Unbounded or unknown size. Exponential search. Uniform distribution. Interpolation for O log n. 2D matrix. Staircase if row and column sorted. Flat binary if fully sorted. Each branch in this diagram corresponds to a slide we've already covered. The tree is the synthesis. The bugs that break binary search and the habits that prevent them. Click Pitfall 1. Off by 1 in the loop condition. While low less than high misses the case where exactly one element remains. Use low less than equals high. And mid equals low plus high / 2 can overflow in C and Java. Always use low plus high low / 2, even in Python as the habit transfers. Pitfall 2. Binary searching unsorted data. The algorithm has undefined behavior. It may return a wrong answer or loop. Binary search requires a sorted array, period. If you're unsure whether it's sorted during debugging, add an assertion. Pitfall 3. List.index raises value error. Unlike dict.get, which takes a default, list.index throws on absence. Guard it with if key in, arranged by first, or use the next with generator pattern. Better yet, use bisect on sorted data. Pitfall 4. Linear scanning a large list repeatedly. Every X in large underscore list is ON. If you're doing this in a loop, convert to a set first, ON one-time cost, then O1 per lookup. Pitfall 5. Sorting before every binary search in a loop. Sorting is ON log n. If you're sorting then binary searching in every loop iteration, you've made it ON log n per query. Sort once before the loop. Click Best Practices. Use bisect for sorted list binary search. Don't implement it yourself. Use set or dict for repeated membership. Use next, with a generator for short-circuit search. Use the binary search on answer template for optimization problems. Assert sorted order in debug mode. For n below 20, don't overthink it. A linear scan is cache-friendly and faster than binary search at tiny sizes. Next. Everything in one view. Click the decision tree, data unsorted. Use set or dict for O1, or linear search for ON. Data sorted, binary search is the default, O log n. From binary, the variants branch off. First, /last occurrence, rotated array, answer space, unbounded, exponential, and uniform distribution, interpolation. Click the one-line Python idioms for the 4 most common patterns. Presence check on a sorted list. Bisect _left, then verify. Short-circuit search. Next, with generator. All indices. List comprehension with enumerate. Set membership for O1. S equals set, LST, key in S. Click. The complete complexity reference table merges everything from the video. The columns that matter for your decision. Time, average, space, sorted requirement. Key entries to memorize. Binary iterative is O log n / O1, sorted your workhorse. Hash is O1, / ON, / unsorted, for repeated lookups. Linear is ON, / O1, / auto/none, always applicable. Interpolation is O log n, / O1, / sorted uniform, best possible on ideal data. Click. The 7 key rules are the summary of summaries. Unsorted, 1 search, linear. Unsorted, many searches, build hash. Sorted array, binary. Unknown bounds, exponential. Uniform distribution, interpolation. Optimization problem, binary on answer. And avoid X in list for large repeated lookups, convert to set. Next. That's the complete guide to searching algorithms. Linear, binary, jump. Interpolation, exponential, ternary. Fibonacci, 2D matrix search, hash lookup, BST and sorted structures, built-in Python tools, and binary search on the answer space. If this was useful, hit like and subscribe. Drop questions in the comments. I read every one. See you in the next one.